Hey everyone, thanks for coming. So yeah, I'm here to talk to you today about language server protocol, the thing that gives us all that stuff in the development environment. So we're going to cover what language server protocol is, the message formats, the messages that go back and forth in that system, how you initialize a language server. I'm going to build a language server, show you how to build your own language server implementation from scratch, and go through things like request response handling, notifications, and then how you actually test and use your new language server inside different editors, because different editors work in different ways. How you can log, and then I'm going to introduce you to the temporal language, which uses all of the features above, and you can rip bits of code from and ideas from to make your own implementations. And then at the end, we'll cover parsing, which is probably one of the kind of challenging aspects of building a language server, is parsing the thing that you're trying to sort of produce autocomplete and so on about. So what is language server? Well, it defines that protocol between your text editor and your kind of programming language. So it provides things like autocomplete. So when you type in your editor http dot, the language server sends a message. The editor sends a message over to the language server and provides a set of results back. You can jump to definitions. So when you go to definition, you're sending a message to the language server, which responds back with a series of potential locations that your editor can then jump you to. And then diagnostics, which tell you when you've written your code badly or produce warnings and so on. And you can also do formatting as well. The language server protocol gives you one protocol for all the different languages. So what that means is, like, prior to language server protocol's introduction, if you wanted to add, say, Go support to a particular programming language, you would have to know about all the intricacies of the Go-specific tooling, which at the time was Go Guru, and used byte offsets and all sorts of things. And then if you wanted to produce the list, there was no sort of necessarily any shared code. So language designers, if they wanted to get the like autocomplete and other features into a text editor, it was quite an arduous process to do that. And for people who are making text editors, it was also every different language was sort of had a different interface and different way of working. So this language server protocol was produced by Microsoft, and they open sourced it as a specification, and it was introduced in VS Code. And Go introduced gopls a little bit later, and that's what you see. That's what you're using when you're doing your auto completion. You probably don't see it like directly as being gopls, because in Visual Studio Code you tend to use a VS Code extension, which provides that feature for you. Language server operates over standard in and standard out, rather than perhaps a HTTP stream like you might be used to if you're building REST APIs. So what is standard in? It's when you do ls, you're typing into standard in, and when you get the results back, that's coming out of the program from standard out. And you can send data to a program over standard in Unix type systems by using this pipe operator. So here you've got this vertical bar, and if you echo your sentence in and do a word count on it, you get the number of words out. But you can actually send any data, so you can send binary data through that. And you can even send structured data like JSON and pipe it through a program like JQ to produce like formatted JSON in your terminal. In the Go programming language, you can get access to the standard in through os.standardin, and it implements the IO reader interface implicitly. So it means you can use that in any function. So you can take in a reader and read from standard in. And standard out is available through os.standardout. So if you write to standard out, that's just an IO writer. So that allows you to use any function in the Go programming language that takes in a reader. You can pass in like the OS standard in and standard out. So here we can decode JSON that's coming in. So put that into the map and then write it back out to standard out through this interface. And that basically provides the same features that we saw in JQ, but in writing it ourselves in Go. So what are we sending over the wire, like over the standard in and standard out? Well, editors can send requests that require a response. So some of those examples of those would be things like the auto-completion results. When you send in a request to the server, you need a response back which contains the pick list, if you like, of items that you can select from. The messages themselves are split into two parts. They have a series of headers. These are MIME headers, much like you'd see in a HTTP request. So they have a key value pairing here. The language server specification states that only one header is always required, and that's the content length header. So you'll always see that in language server protocol messages. And then you have an empty line. So if you imagine piping this value into your program, that's what the language server is doing. The content part then contains a JSON RPC formatted message. So it's as the name suggests, JSON RPC uses the JSON format. So that's the structure of it. You can see that it's JSON RPC because every JSON RPC message contains this key called JSON RPC and the value of 2.0, which is the value of that spec. And every JSON RPC request message includes a method as well, which says, what is the thing that I'm trying to do inside the language server. So in this case, it's get to the declaration. When the editor is sending a request where it expects a response back, it always includes an ID field, and the ID field is then included in the response message, and that's how the text editor knows that this response matches up to the request that I made, and we'll see why that's important later. And the request messages can contain arbitrary parameters. So in this case, the specification details exactly what's going to be in each request that's going out to the language server. But it's pretty straightforward. There's a header containing some HTTP headers, and then there's a content part containing some JSON. The response messages we're going to send back are actually in the same format. They all start with this content, with this header section, which always contains the content length. And then it says JSON RPC. It returns the ID back that we got in the request, and then it always returns a result property containing the result of that RPC call. So in this case, we asked for where is this defined, and we receive back a range to say that's its location in the source code. So your editor will then bounce you to that location. Editors can also send notifications. So those notifications don't require a response. So examples of notifications are things like, hey, the user has opened a file. Here is the file that they've opened, and here's all of the contents of the file that they've opened. So if you imagine in your editor, you might not press save yet. It might be a new file. So the language server won't know about that file. It can't just read it off the disk. The text editor has to notify the language server, hey, this is what the user is seeing on their screen. And servers can send notifications back the other way. So you might send back to the editor diagnostic information, so warnings, and those can come at any time, and you can also send messages back to the user. So we'll see an example of some of these notifications in a minute, but you can, they can be sent at any point through the cycle. Notifications are basically the same format as requests, but without an ID, so they have the content length, and then they have the JSON RPC field and the method field, and then there's no ID field, just parameters. So that tells you that there's no response required to that message. So you've got the JSON RPC field, the method, and the parameters. Unlike kind of typical HTTP request flow, messages can be interleaved. So if the editor sends in a request, the next thing that comes back on the wire might not be the response. It might be a notification back from the server. It might be some other element. So you can send a few requests in rapid succession to the language server, and then you'll get them back, and it's up to the editor to sort of consolidate that. The specification says that they should be roughly in the same order when you get them back, but it doesn't clarify on exactly what that means. But in practice, the messages themselves include version identifiers, which identify the version of the document that the user is seeing. So generally, the editor can use that to work out whether they should discard the message or not when they receive it back. The spec defines the requests as TypeScript interfaces, which is slightly awkward for anyone who doesn't know TypeScript. It makes also extensive use of TypeScript's extensive type system, including a lot of inheritance. So, for instance, these things here, these vertical bars, are basically says that an ID could be an integer, but it could be a string. It could be either one of those types. And the params could be an array, but it could also just be an object. And the question mark says, yeah, well, it could also be null as well. It gets worse. So But for us in Go, we can say, actually, well, for the ID, we don't really care about what the ID is. All we need to know is that when we return a response back, the ID is the same as the request, as the ID in the request. And so we can use JSON raw message to say, like, look, don't bother, just whatever value it is, we'll just chuck it out the other side. And we can do the same with the parameters to defer the loading of the parameters. So we only know what type or shape the parameters are going to be once we've read the method on the incoming request. So if we use a raw message, we can defer the processing until a little bit later. So that's my Go definition of what a request message looks like. So to read a message, we can read from standard in, which is, as I said earlier, an IO reader. And there's a couple of things we need to do. First, we need to read those sections of headers, that content length and then the empty line. And Go standard library includes a tool for doing it in text proto. So it's actually just one line of code to do that, and that's relatively straightforward. It takes in a buffered reader, so I've updated the functions taking a buffered reader instead, but it's relatively easy to do. Then I need to parse the content length header. So we know that the content length header should always be there, and in the specification it says, like, if the content header isn't there, it gives you a specific error response to return. It's just not a valid response. And then we can make use of a limit reader in Go, which you can pass it a reader and say, read this many bytes from this incoming stream of data. And we can pass that into the JSON decoder and decode the value, and away we get our message. Finally, we can check for the presence of the JSON RPC field, make sure that its value is 2.0, and if it isn't, we can start complaining that, I don't know what you've sent me, but it's definitely not this, it's definitely not an LSP formatted message. So yeah, the response messages are also defined as TypeScript interfaces, and I did say it would get worse. And what this means is the result is quite flexible. It could be null, but it could be a string, number, Boolean array, or an object. So what that really means in Go terms is any, right? So if you look at the JSON, like the JSON Marshall interface, it returns like an any result. So what we've got there is just in any. We don't really mind. We're just serializing the results back, so we can be quite abstract in what we're doing here. As I said earlier, we don't need to process the incoming ID. We just need to make sure we always use the same ID. So it doesn't really matter that it could be a string or an integer or a null. As long as we put the same result back. And writing a message is even easier than reading one. We marshal our message into memory first, so that we can work out the length of the message. Then we can write the content length header ourselves, and then write the body out, flush the buffer, and we're good. So at that point, we've got everything we need to read and write language server protocol messages, but we haven't got any custom code to deal with those messages. So let's implement a multiplexer, just like the HTTP serve multiplexer, and then that will allow us to wire up individual methods to functions that have an implementation. So first, we're going to map the method names to the handlers. We're going to create the multiplexer and pass it a reader and writer, which will be our standard in and standard out. And then I've defined here two functions. One defines any function that matches this signature is a notification handler, and it's going to take in the parameters, and it's going to return an error. No result, because if you get sent a notification, remember you don't need to do anything with that. You don't need to return anything back to the server. And also a method handler. So a method receives parameters and returns some sort of result back to the language server client, in this case the editor. And so then it's a case of making a map between the method name, which could be like text document, or it could be did open. So like, I've opened up a text file. So you'd add that to the handle notification, and so that's a mapping then of that method name to the function that implements that behavior. We want to be able to send notifications back to the text editor. So the multiplexer also contains a notify method. The notify method has a mutex on it. So a mutex is a way of making sure that two things aren't trying to use the same resource at the same time. So the write function locks the mutex and then defers an unlock of it, executes the write operation that we saw earlier. And that allows us to build up then a notification which says, okay, I'm going to notify back to the text editor this method with these parameters, off you go. If we didn't have a mutex, we might have this sort of scenario where like two things are operating in parallel in Go routines and they both try and write to standard out at the same time. You might end up with this kind of scenario. So there's no guarantee in an IO writer that that two things won't try and write at the same time. But with a mutex, you can make sure that the messages are ordered correctly so that you only get a complete message through. Final step in our multiplexer is to process those messages. So we need to start up something that's going to read from the standard input, bring in those requests, work out whether it's a notification. If it's a notification, grab out our handler and execute it. If it's a method, let's grab the method function. If we haven't got one, then we have to return a response back to the editor to say, you've sent me a message that I can't deal with. And in your text editor, you'll see like a warning, usually saying like, you know, the LSP has said they can't handle this. If you do have a handler, you can execute the handler, and if that fails, you need to return a response to the editor to again say like, well, something didn't go right in whatever I was trying to do. And if it was successful, then you can return the result. So the key thing about returning the result is, you know, including the ID that you got from the request, and then passing the parameters. And because it's Go, we can easily multi-thread this operation by adding a Go routine in this one. So as soon as we've read the message, we're then free to throw that onto a Go routine, and you know, it'll process when it's good and ready. You might want to control the concurrency in a more realistic scenario. So the sample code that I'll show at the end has some concurrency controls to limit the amount of concurrency that you've got running on. Right, covered a lot in those 15 minutes there. So let's like have a quick summary of that. So LSP messages sent over standard in, standard out. The messages consist of those MIME headers with JSON RPC. We've got that correlation ID, so the ID of the request and the ID of the response have to be linked to each other. The text editor doesn't need to wait for a response, they can be interleaved. And we can send notifications in either direction. The editor can send a notification at any point, and also the LSP can send a notification to the text editor. And now we've got this mux type that you can use to wire up these method types into something a little bit more you know, actionable. So the language server protocol also, like now we've dealt with the kind of wire behavior, like the sort of how messages are transmitted. We're going to go to the next level up, which is there's a sort of initialization handshake at the beginning of a session, essentially. So when you open up a new project in your text editor, the editor will start up the LSP server, so it's going to start your program, and then it sends an initialization request over to your language server. That initialization request includes its capabilities, like the things that it can do, and the LSP returns an initialized result, which says, well, okay, I've heard the things that you can do, here's what I can do, and between it, those represent the capabilities of both ends. So as you can imagine, we're on, I think, language server protocol version 3.17, and they keep adding new stuff all the time. So like I think one of the latest things that they added was a sort of, I can't remember the name of it, but like in function parameters, you can add a little bit of text next to next to a function parameter. So there's like new stuff being added to the protocol all the time. So what you might do is say, well, I can't handle that, or I'm not interested in handling that. And that means that you can write a fairly minimal language server. You don't have to take on the whole of the specification. You can just say, look, I can only do these one or two things. And you can still get value out of a language server that you create. Finally, the editor says, okay, I've got everything, I'm all set up, and then it sends an initialized notification back to the language server. And at that point, you're in sort of free-flowing territory. You can, you know, receive and respond with any type of message. So after this initial handshaking, you're basically good to go. More TypeScript, as we know, because it's all defined in TypeScript. So here we've got an inheritance of work done progress and so on. And I think this is probably the most frightening part of language server is the sheer volume of types and the size of the types. But the key thing that we're really interested in are the client capabilities, which is, it is absolutely huge as a message. So it includes all of these things like, you know, can I handle workspace edits? As in, like, if the language server returns an edit, can the text editor actually process that edit? So can the LSP trigger changes to the text documents? So I've brought out some of the kind of most important fields. So things like the inlay hint, which is that's the thing I was talking about inside parameters, which gets it added in, and also diagnostics, which is like compilation errors and warnings and that sort of thing. So those are probably the most important ones, I think. But again, we don't have to take on the whole of the specification to provide value and to create a language server. So we can just take out, just from the client capabilities, what we want. So here I've just said I don't really care what the client is. I'm just going to receive anything. I'm just going to assume, make some assumptions about the capabilities of the language server. So the capabilities I'm going to assume are that it can handle some of the messages that I'm going to send back. But if you're following the specification to the letter, you should be receiving those client capabilities, and then before you send a message back or a notification to the client, you should check that the client can actually deal with it. Otherwise, the client will just reject the message. The server capabilities are a similarly complicated, labyrinthine set of TypeScript. But again, we can reduce that to just the things that we're interested in. So if our server supports things like completion, we have to say, yeah, by the way, this language server that you're communicating with can support completion. And one of the most important things is synchronization of documents. So when the text editor opens up, when you open up a document in the text editor, it'll send a did open notification to the language server containing the full text of the thing that you just opened. And that's great. But then after that, as you start typing, you haven't pressed save yet, right? Like it's in a kind of unsaved state. And the language server needs to be notified about constant updates by the text document /did edit notification. And there are two modes that the client will do that. One is that it'll send the whole document every time, which is great because it's really simple for a language server then to say, well, I've just received the whole document. Or you can also do incremental updates, which is better for performance. So in that case, the text editor will say, oh, the user has just added enter in this particular spot, or they've just deleted this range of text. So in my example code today, I'm just going to use the full text of the document because that's the simplest implementation. But if you look at the language server that I'll share at the end, you can see a mechanism for dealing with incremental updates, because it was probably like the buggiest bit of my code was sort of dealing with sort of partial updates to text files. So I took a look at some of the other implementations that were out there, like the JavaScript one and so on, and came up with one that works really well in Go and performs better. So we need to implement the initialize handler. So this is a method. We need to receive these requests in and return that response back. So we've got these initialization parameters. So we need to start up our multiplexer on standard in and standard out. Register our initialization handler. We can unmarshal those params and then return our results and say, okay, right, please send me the full text every single time that a user makes any changes to it. And by the way, I'm called example LSP. Then we just go in a loop and listen to messages until standard input is closed. So very straightforward for us to then sort of add on additional messages. And then the final kind of bit of the handshake then after the initialize method is when the text editor sends us the initialized notification. And so we can do something interesting at that. So the kind of hello world of a full language server implementation would be to handle that initial handshake. And then when we receive initialized, we can start looping around and using window/show message to make a notification in the text editor. So I guess the most useless LSP in the world would be like, you know, hey, you spent 20 minutes coding. Maybe you should stand up or something. Right, so let's go again. So let's go for a quick summary then. The text editor sends that initialize request. The LSP returns a response that has its capabilities. And then afterwards, it sends that initialize notification. That's the handshake of the protocol. Before using the capability, you should check to see whether the client supports it or not. And we can start sending notifications back to the client with that notify method. And we've got like a hello world. So it's great, but how do you actually run the thing, right? Like you've got a language server. That was actually one of the challenges of implementing it, because it talks a lot about the protocol, but not about the realities of how you actually test these things. I think about 20% of the Go community using Vim or variants, and it's actually the simplest implementation is actually to do it in Vim or Neovim, because Neovim, as of I think 0.5 or 0.8, includes language server support by default. So you can add a bit of Lua to your initialization, and this says, like, if there's a file called .example LSP in your directory, then start up the example LSP program, and as long as that's in your path, that's all that's required for Neovim to provide basic LSP capabilities. And you can start up a Neovim with like this -- clean to get rid of all of your other configuration that you might have, and then you can test it in Neovim. So if you do that in Neovim, you see this kind of ugly thing at the bottom that shows you what's going on. But for people who like Neovim, that's like awesome. Visual Studio Code is probably the most popular text editor for Go users. And yes, you're not going to like it, but there's more TypeScript involved. So in Visual Studio Code, you have to create a Visual Studio Code extension which calls into your language server. But actually, this is the entirety of the code. Although when you create, like, if you follow the instructions from Microsoft's team there on how to do it, it generates like a big project, but actually the extension TS where all the action happens, it's only a few lines of code to get it going, and it's basically the same thing, right? If you have if I have a file with a cook extension, then it'll start the example LSP command, and as long as that's in your path, it'll work great. We can also tell it that we want to use standard input, standard output for LSP, because it is possible to use some other mechanisms to communicate. We then create the client with those server and client options, start it, and we're good to go in VS Code. You can also, the other thing you've got to do is update the package JSON to add in the language client. So that's the code that starts at the language server implementation, and then tell it to activate when you open a .cook file. So that's the activation events. And you can also provide like a language configuration and syntax highlighting rules inside the same Visual Studio Code extension. So the configuration defines things like closing brackets. So if you open up a bracket in your language and you always expect it to auto-insert a close, you can apply that in there. And that can help with parsing later, because it means that your object model is more likely to be correct. We'll go into that in a little while. So once you've created one of these things, if you open up your extension project and hit debug, it starts up a new VS Code which contains your language server, which contains your extension and is ready to configure. So I'm going to show you how to make a LSP for the cook language, which is about making recipes, because it was a relatively straightforward thing to sort of explain. JetBrains last month just announced support for language servers as well. So prior to that, I think you had to do your own kind of thing in JetBrains, but last month they produced this. So again, you have to create a plugin, and in JetBrains, the ecosystem is Java, so it's kind of in Java, but you can see it's pretty much the same behavior as what we're talking about with the TypeScript one, right? And indeed with the Lua one. It's just, does this file extension work? If so, run, the language server executable and communicate over standard input, standard out. So basically, you should be able to support all three major editors without much fuss. So let's build an LSP for cooklang. Cooklang looks a bit like this. You've got then add salt and ground black pepper to taste, and paste a kilo of bacon strips on a baking sheet. So what we've got here is, if you, ingredients start with an amphora or @ symbol, and the ingredients end with either a word boundary, or they go all the way to these curly braces. And inside the curly braces, we can have quantities, like birr quantities, like, so you might have @ eggs and then 3 inside the curly braces, or you might have a sort of unit or a quantity. You can also describe required equipment like a food processor, and you can put timers in as well, so that they have a similar behavior. Somebody made a parser for Go already, so let's use that. And that allows us to do things like look for really silly measurements, like American measurements called cups, sticks. What are these? No one knows. What is a cup? So if you can parse the recipe, you can look through the steps, look at the ingredients, and complain if somebody's using non-SI measurements. Although, to be fair, in Britain, we are slightly on we're a country that measures, fuel in litres and then distances in miles, so who knows. Cook-Lang-Go internals, it passes line by line, but it doesn't have a structured error, so it basically includes the line notification as just text in an error message. If you're building a parser and you want it to be used in a language server implementation, it's much better if the error includes a range, like a start and end of where the errors are, because that then allows you to place those errors in the user's text editor interface. So if you can include a more structured error and include the start and end positions of those, it makes the job of writing the language server much simpler. And also, if you include the if you're parsing into an object model, if you include the range of where that is in the text file as well, that allows you to sort of iterate through the object model and look for different positions and say, well, is the user's cursor inside this object or not? Helps you to do like autocomplete and lookup. So so we've got the handshake done earlier. Now we need to handle opening up the file and returning diagnostics. So when the editor opens up a file, it says, text document did open. You can parse the document, find any errors, and then return. Well, it's not a return here, sorry. You can send then a set of diagnostics down to the text editor for them to display. So the did open notification, oops, wrong one. The did open notification includes the content length, like we saw earlier, and then it's basically the full text of the document you just opened. And then, given the user might make some changes to that file, right? And those haven't been saved to disk. So the did change will also then include the updated document as well, and then we can push the same diagnostics. And the did change is basically the same structure as the did open, except it's got an array of content changes. So you might receive more than one content change if you're receiving like partial updates. So like, oh, the user added enter here, they pasted this section in, they deleted this line. You might receive a block. But in our case, because we told the text editor, hey, we can't deal with like partial updates, just send us the whole document. We're just going to get the whole of the content in the text, and that makes it much easier for us to implement this. So we now want to start processing this stuff and dealing with these changes that we're receiving as a language server. And so we can start, we can make use of Go's concurrency here to make a channel that contains a list of, that's going to receive updates to the documents. And then as we receive those updates, we can start finding our diagnostics. So, and then notify the client about the diagnostics. So that means like if we get a parser error or if we get like quantity errors or other information, we can notify back to the text editor and the text editor can display them. So we need to register some method handlers, so some notification handlers, so like to receive that open text and change text and push those into our queue of changes. So it's a case of subscribing a handler that's going to send notifications and then also handling those notifications and pushing them into that queue. The diagnostics themselves then are fairly straightforward. We can start to do things like parse our cook language, and if it's our cook-lang error, if it's not it, like we can then start to look at the ranges of that and then apply those errors to the text editor. So the first thing is to parse the text, check the type of the error, like is this an error that's coming from the parser or is it some other type of error? If it's not, we can't read the ranges. And then we can start to apply diagnostics. So we can say, right, okay, this error is happening in this location, and we can pass the error message straight to the user. I also created a swear word diagnostics, which just it doesn't parse the text. It just uses like a list of known English swear words and says, you've included a swear word in your document. Very straightforward to do. And even that simple language server gives us the ability to do things like this. So invalid block comment, so showing you straight away before you've even saved the document that you've got invalid syntax in your file. And you also get timer syntax because these are already built into the parser. So even if you're working like in a small language like D2 or like GraphViz or something else that already has an existing parser, you can provide like a lot of value by making this minimal type of LSP and just shipping back the errors straight to the user. And then that just brings those errors so that they're not waiting till they've hit save on the file and gone to the command line and run an extra command. You're bringing that to them a little bit earlier. So yeah, in summary, it's possible to make an LSP for pretty much anything that has an existing Go parser, or and you can pass that into an object model, and then use that as the basis of your like notifications back to the user about like where the errors are in the file. If you include those file positions in your object model, then it makes it easier to display the diagnostics in the correct locations. And you don't need parsing to succeed to produce some diagnostics. So like, you know, it's helpful if you support like partial failures. So like have a good go at parsing through the document and still return like a list of errors back to the user. So let's look at autocomplete. So it should be pretty familiar by now, I think. Like, you know, you're probably getting the idea that there's methods, there's notifications, and each method has a name, each notification has a name. So it's basically the same process. We need to add a new method handler to our multiplexer. In this case, we need to update our initialization to tell the text editor that we support auto-completion. So in this case, we can set the trigger characters. So we can say that when you type in your text editor a percent symbol, that should trigger the text editor to send a autocomplete request to the server. And that's done at the initialization stage, so when you're setting up the client server capabilities. And then we can, the other thing we need to do is update our change handling. So as we receive updates to those text documents, when we get to receiving the autocomplete request, we don't receive the text of the document. So we have to keep in memory somewhere the current text of the file so that we can look at the correct place for auto-completion. Or we have to continuously keep a cache of like where auto-completion requests would be successful within the LSP. So at some point you have to essentially cache what's coming, like the text changes that haven't hit disk yet. And then we can implement the completion itself. So the completion parameters include like the name of the file that the person is in at the time that they're asking for completion. And then we can start to look for completion items in the position that we've received from the user. So in this case, if I look through each of the steps in the recipe and look for each of their ingredients, I can then say, well, if they're inside an ingredient and they press percentage, they've got to be in the unit of measurement area, and then I can send them back a list of potential measurement units, so milliliters and kilos and stuff like that. The parser needs to return something useful at all times. So if you're making a parser, like as you're typing at pizza and you put in the curly brace, you've actually got an invalid cooklang document at that point because you haven't got the closing brace. So earlier I showed that you can trigger the text editor to insert automatically the closing brace, and that would give you a completely valid document. But you should also be able to handle the case where, you know, I've opened up a brace, but I haven't completed the brace. You still need to be able to produce auto-completion results at that point. You can't just throw an error and complain about it. So in this case, when I use cooklang.parse, it returns an error of unterminated quantity because, yeah, the quantity isn't terminated. It doesn't have a closing brace. But it also returns a range that says, yeah, but we know really that there should be a quantity at this point. So that's going to be the range where if the user's in that and they trigger auto-completion, I do want a full list of results coming back. Neovim, like always, makes it very straightforward. It's a simple Control-X, Control-O to trigger auto-completion to show up. Or you can introduce nvim comp. But Visual Studio Code has it built in. So straight away now we're seeing auto-completion happening there. So when it knows that you're in the sort of ingredient section, and it's then able to provide you a list of valid quantities. Right. So most of the time in my kind of day job of making APIs, REST APIs or JSON-ish APIs, you're generally logging to standard out, right? But we can't log to standard out here because standard out and standard in is being used by the communication for the language server itself. So typically what you want to do here is enable some sort of logging to a file so you can see what's going on. With the new slog library, you can create a file, pass that into slog, and then use JSON logging. And then inside your handlers, you can log the parameters that you're receiving from the text editor, and that's really useful to be able to see what you're getting from the text editor, so that you can interpret what your results should be coming back. Over the last few years, I've been using these techniques to build a templating language for Go. So I started it in 2021, and it's kind of like JSX in the JavaScript ecosystem, or Razor Pages in C#, but for Go. The uptick there is a Reddit post. Basically, if you want to publicize your stuff, stick it on Reddit. It seems to work. And it's strongly typed, it's compiled, and I wrote it so that it would support LSP implementation, so you could get like autocomplete and stuff when you're making HTML pages in Go. It's designed to work with HTMX, which is all over Twitter, worth a watch. And been using it over an insurer to produce all of the PDF documentation that you get when you buy car insurance. So I think most people go, well, why would you bother? Go has templates built in, right? Like these ones here. But actually, this Go template will fail on program startup because I didn't register the toUpper function as a function map into the Go templating language. And also, this one will fail at runtime because I referenced a price field, which doesn't actually exist in the struct. So this is a problem because what we're trying to do with the whole point of having things like editor implementations of language servers is that you get feedback when you're typing before you've even hit save on the file. And if you're only failing when you're in production, then it's much more expensive, much more difficult to deal with. Even if it fails at CI/CD, that's like 5 or 10 minutes before you've found out that. You could have maybe dealt with that a little bit sooner. And you don't get any syntax highlighting or IntelliSense. I know that there's some work happening around like a language server for the Go templating language, but it doesn't seem to be working for me. And maybe it's also much faster as well. But when you're talking in nanoseconds, right, it doesn't really matter, I think, for most templates. So yeah, the language itself is fairly straightforward to read. It looks like Go code, but with HTML in it, because that's what it is. And you can define like the types that are passed to a template by it looks like a function, because that's what it is. And you can then use the name in scope, and it will kind of output the results. So inside those braces, that's a Go expression. So outside of it, it's HTML. Inside, it's Go. And you can call templates with each other like function calls. And you can use normal kind of Go constructs like if statements and so on. The way it works is when you generate it, it generates a Go code. So you use temple generate at the CLI, and it generates a Go file that outputs all of the HTML and does all of the interpolations. And that gives you compile time errors and so on. That makes it relatively straightforward then to create a VS Code extension. So here it's aware that the last name field doesn't exist on that person because the Go code isn't working right. And the way that this operates is that it uses it wraps the Go LSP itself. Because if you think about it, that position there on line 9, the Go code isn't failing at that place, right? The Go code is failing at a completely different place in the generated code. And what Temple does here is it creates an LSP implementation and then parses the Temple file, works out which bits of that are Go code, and well, it generates then it generates the Go code and produces then a position mapping of where that Go code is related to the Temple code. It then communicates with Go, please, the Go language server, and returns the results back and remaps those positions. And what that allows it to do is make use of the Go language server. So you can do that with other languages as well. So if you have if you have a programming language that or like a templating language that then wants to drop into other sections, you can proxy in between different LSPs if you wish. And another debugging technique that you can use is, although standard in and standard out is taken, you can still start a web server. So internally within Temple, it can start up a web server which allows you to inspect what's going on inside your language server. So in this case, it keeps a mapping of all of the. On the left-hand side, you can see the Temple code, and on the right-hand side, you can see the generated Go code. And the green bits are the mappings in between the two things. So you can see in real time, like as you're editing text, you can go onto the web server and kind of inspect it. So that's a really useful technique if you're building your own language server. Is put stuff like that into your tool so you can see what's going on inside. So yeah, hopefully from that you get the idea that the idea is to move the notifications earlier to the developer, and you can also piggyback on other LSPs. So if there's an LSP that does what you want and you want to use bits of it, you can probably proxy in between those two things, and you can have a look at Temple's LSP to see how to do that. Feel free to start up a web server for introspection into your tooling, and of course pprof can also be attached to get like information about what's going on in your language server. I guess the challenge then of dealing with the language server then is parsing the input in the first place. So the Temple language that I mentioned earlier uses this parsing library that I wrote, and it defines an input, and then the input has essentially a pointer to a location in that string. So its initial position would be 0, and then as you successfully parse A out of the stream, it moves the index to 1. And then as you do B, it goes, okay, I'm now at position 2. And then if you fail to parse, it doesn't move the position. It's like, no, you didn't get it. So with that, you can then start to stack up these functions into sort of bigger parsers. So here's a parser that's going to look for 4 digits in a row. And you can say, okay, well, I'd like to parse that year. And here you can see it's returned the result of 2000. It's parsed successfully the first 4 digits. So it's equivalent essentially to the regular expression of \d with, brace 4. You can also then create like parsing to objects. So it uses Go's generics. So you can create a parser function that like passes into a time struct instead. So here I've got a year parser that will look for 4 digits, use that 4 digits, attempt to parse. If it's unsuccessful, it'll wind back to where it was at the beginning of the parser. So it's a recursive descent style. And then it will return a date if it's successful. This is what Temple uses to load into its own internal object model. So if you imagine like the sorts of things that you're going to have in a HTML document, you're going to have HTML elements. Those elements are going to have a name. You're going to have attributes on those, HTML attributes. Those attributes can be of lots of different types. So they could be like expression attributes, Boolean attributes, CSS attributes, different types of attributes. So there's an interface that defines those. And then inside your element, you might have like a series of nodes. So those nodes might be if statements, but they might also be other HTML elements, which they then themselves contain a tree of elements. So we want to create like an object model that contains this kind of document so that we can provide that LSP functionality. And so it uses this parsing library to do it. So a self-closing element is like otherwise known as a void element, is one that has like a closing slash at the end. So the parser for that would work out what its current index is, and then attempt to parse the less than symbol. If we're unsuccessful, we can just exit. Like, hey, this is not, at this location in the file, there's no self-closing element to be found. Then we can try and get an element name. So if we don't, like an element name consists of like a non-digit, so a non-digit like a A to Z type character, followed by a number of different other characters, including like hyphens and colons and such. And then we start to bring in the attributes. If we fail to get any of these, we have to seek back and wind back our parser to where we started, and we can return. Finally, we'll get some optional white space, and then we close up our void element. And building parsers in this way lets you create unit tests of individual like blocks of code. So for instance, parsing the anchor tag here, I can check that the object model that I get back is what I expected, and that the ranges of the expression there are in the correct place. And that's one of the ways that it makes it fairly straightforward to identify which bits are Go code and which bits are sort of HTML code within the object model. You can then again build these up into higher level and higher level parsers, so that you can have like an element parser that sort of again does the same thing. It works out its current position, tries to parse an element, like is it self-closing or is it an open-close type element, and then after you've parsed it into that object model, you can start to validate it. Like, what problems are we seeing inside this? Like, do we have any empty attributes? Do we have any other issues? And we can return a parser error there. So this library is like a bit of an alternative to tools like Antler or PEG tooling. So if you've kind of seen parser expression grammars and so on, like you might find them a little bit intimidating. And also they tend not to produce extremely good errors for users. So if you're trying to build like a little language and provide really good errors for people, it can be quite challenging to do that. So this technique uses like a parse input which keeps track of that position, and the parse error which returns exactly the position of where the errors occurred, and it helps to provide good messages to users. So yeah, again, this is a way of building up small testable parsers that you can use then in your language server implementations, and this pattern lets you compose small parsers into bigger ones, which has allowed me to sort of maintain the project quite successfully over a couple of years. Like, it's quite easy to add new things in with a really good solid test suite, and when I get an error, I can kind of see where I'm going wrong. So at the beginning, this is what we said we covered today. So it's like, what is the language server protocol? So if you remember, we went right down to the basics of like the wire protocol itself, like the headers, the JSON RPC body, and how the ID is mapped between request and response. We went through notifications and methods and how those are different. We went through the initialization handshake, how the LSP client has to tell the server like what it can do, and the server has to tell the client what it can do in return. And that's how that begins. And then we've got request response handling of how we have to deal with the did open request and the did change requests and return responses back to that. And we also showed a few notifications, like how we send notifications back to the editor to include things like diagnostic information and so on. Covered a little bit there on how you use the LSP in an editor. So in Neovim, setting up the Lua configuration, in VS Code, creating a VS Code extension, and in JetBrains, using Java to create a plugin for Golang or similar. And then we talked a little bit about logging, like we can't use standard input, standard output. Don't just try and log stuff, you'll just break the LSP. You need to log to a file instead and pass a logger around. Then I covered a little bit about the Temple language, how it uses some of these techniques, and then went into some detail on how you can build up parsers that will allow you to sort of parse those object models and build up your LSP implementation. And so what I'm hoping is that people who are like using a language like the Nix language or D2 or lots of other different small kind of text-based languages will kind of find it a little bit more accessible to build up like these text editor plugins that I think are really valuable for helping developers to be efficient. I've got some resources here at the end. So this is like the slides for the talk are available there on GitHub in Markdown format. We've got the example LSP, all the source code there if you want to play around, build your own LSPs on that. And there's some links there to Temple itself, and you can, inside the Temple LSP, you can see some really, that's where this partial update handling is. So if you're interested in sort of getting really efficient LSPs, you can see how that works. And the parser library there as well, and also the lsp.dev. So there's a team out there who've built all those complex TypeScript object models that I showed you earlier with the bazillion parameters and so on. This team here has built a Go package which contains all of those defined as Go structs already, so you don't have to sort of tackle that yourself, basically. So yeah, thanks for coming along, and I think we've got 5 minutes, maybe for questions as well, if anyone's got anything to ask.